Excellent.
Sure.
So the next speaker will be starting in about 2 minutes. It will be Sven from University of Lancaster, talking skill verification of distributed synchronization. And there's Sven, excellent.
Okay, so I think you should be able to see me now and also see my slides, right?
Absolutely, you and your slides both, fantastic.
Perfect. So I'll start in a minute, right?
Yes, if people move between sessions, I don't know how many parallel sessions we're running at the moment. Then
that makes sense.
We'll start.
Sure.
We'll run on time. Yeah. So yes, thanks also for putting on the slide what we haven't put in the program, namely when was this published? November 2020 in Formal Methods and System Design. Broadly speaking, we've looked at the panels looked at all the papers published in the 3 journals: Formal Methods, System Design, Science of Computer Programming, and Formal Aspects of Computing. Between the previous journal First Track, the previous FM conference, and just before this one. We filled the time. Over to you, Sven.
Okay. Great, thanks a lot for that. I actually realized that it was on the last slide, so thanks for pointing this out. So I'm presenting joint work that I did with Paul Gaynor, Claire Dexon, Ulrich Hustad, and Michael Fisher that we did while we all were at the University of Liverpool. And the topic of the whole thing is about how to synchronize decentralized systems. And you can imagine, for example, the system of small little robots, and these robots can push something in a direction, but they're very weak. But they should push, for example, a very heavy box. And the way they can achieve that is if they all push at the same time. But because that's a distributed system, they need a way to actually synchronize, and that means they need to push at the same time. And another example would be within wireless sensor nets, where you need to ensure that nobody wants to send at the same time. That means they need to know when the duty cycle starts. And also they need to be able, for example, in smoke monitoring or other applications, to take samples at the same point in time. So again, you need to synchronize them. And there's a certain model that has been used, and that's inspired from biological systems, and that is a so-called pulse-coupled oscillator. And by oscillators, we mean that these machines or these things internally follow some kind of cyclic pattern. So that means it starts from one value, goes up to a certain point, and then begins at the old value. And then these oscillators may influence each other at discrete points in time. And we call that a firing. Whenever one oscillator fires, it will influence the other oscillators that perceive this firing. And generally, this firing will happen at the end of their cycle. There are some other notations, and I think the most important ones are the perturbation function, which determines how the oscillators actually react to the firing. For example, they may increase their own phase linearly depending on their own phase, the number of oscillators that are firing at the moment, and also some other coupling constants. And finally, there's also something called the refractory period, which means some part of the cycle where the oscillators won't be perturbed. So they won't react to any firings. That's something taken from biology, and it works out quite nicely in this model. In our addition to that is that we also assume that these things may fail to fire, and that we assume that that the oscillator that wants to fire just has a probability of not firing at all. So the failures lie within the firing, not within the perception. So for example, imagine 2 oscillators here. The time goes from left to right, and the phase for each oscillator goes from bottom to top. And you can see that they start out in different phases. So oscillator B is in a higher phase, half its cycle, than oscillator A. And so then time progresses, they both increase their phase, and at some point oscillator B fires. And then you can see that it perturbs oscillator A. Oscillator A increases its phase, and then both go on further. Oscillator B resets its phase, and at some point oscillator A fires, and you can see that oscillator A then also gets perturbed, but to a lesser degree. And then after a while, at some point, they actually fire all at the same time. So they are actually synchronous after a while. If we added a refractory period, just to give you an example how this may affect this whole thing, the beginning is the same thing. This time, both oscillators have a refractory period of, well, let's say, up to 2 points in the cycle. And in the first firing of oscillator B, nothing happens, it's the same thing as before. So oscillator A gets perturbed. But then when oscillator A after this fires, oscillator B is at that moment still within its refractory period. So you can see that there's nothing happening when oscillator A fires. And then afterwards, even already with the next firing of oscillator B, they are already synchronous. So actually, refractory periods, if they're of a reasonable size, may help the system to synchronize faster. So what we are doing in this network, because we're looking at computing, we are actually looking at networks of pulse-coupled oscillators with a discrete time cycle. Traditionally, in biology, the time cycle is actually the real values between 0 and 1. But since we're working with chips, basically, and finite amounts of memory, we assume that we have a discrete time cycle. That gives us some other assumptions, and that is that all of these oscillators actually operate with the same speed. So they may work in different cycles at different phases, but they actually will progress with the same speed. And also we assume that the oscillators may recognize that our oscillators fire and also may fire within the same time step. And this means that if an oscillator fires, it may actually perturb other oscillators also to fire. And these, again, so we can get something like a cascade of firing oscillators. You can see an example here where the oscillator on the top is firing and perturbs the oscillator on the left enough to fire as well, which then in turn, because now we have 2 oscillators that fired, perturb the right oscillator to fire as well. And all at the time, oscillator 1 didn't react to this at all because it was in the refractory period all the time. Okay, so within this kind of model, we actually asked us 3 questions in the paper. The first one is, how can we formally model these networks? Would be nice if we can formally analyze how they behave. And the next question that, of course, came out of that, how can we actually efficiently analyze networks of such models, of such oscillators with varying parameters? So where we are changing the duty cycle, for example, or we are changing the amount of failures, the probability for failures, or the perturbation function, and so on. And the third question that we asked ourselves is, so up to now, we always think about, do these oscillators synchronize, or does the network synchronize? And we actually asked ourselves, are there more interesting properties? And these 3 questions I will address in the rest of the talk. So first of all, the question to the first is, of course, yes, because it's relatively easy to write down a model in terms of discrete time Markov chains. We have discrete steps in the duty cycles. We have just probabilities, and the behavior of an oscillator only depends on what is currently happening in the model. So you can basically give every oscillator a set of phases, 1 to t, where t is the maximal phase, and at that phase it will fire. And if an oscillator increased its phase up to this level, we'll need to check if the other oscillators are perturbed enough to fire as well. Of course, that means we need to check for these cascades. And there we need to do a bit of tricky modeling. What we actually needed to do was to add 2 internal states for each phase, in which we encode whether we've already perturbed this oscillator or we haven't yet. And this allows us to basically check one after the other in the oscillators whether they would fire while being perturbed. And we also keep track in the amount of oscillators that fire in a global counter. So whenever an oscillator fires, it increases the global counter, and then we go down the number of phases with the other oscillators to see if there are other oscillators that are now perturbed to fire. And you can actually model this directly as one huge single DTMC. And why would you do that? Why won't you just create different parallel DTMCs and create some good parallel operators for that? Well, the reason is that perturbing the oscillator depends on how many oscillators you actually have in your model, but also how many of these are perturbed enough. And this may actually have an impact on new oscillators that you add to the model, but when you add these, this will impact the other oscillators that you have in your model already. So there's no nice, sensible way to actually define parallel product here. However, if we look at that, there's a straight way to formalize this or implement this within, for example, the language of Prism. So we can actually translate each oscillator, all the oscillators into single modules, and then encode the transitions according to the possible numbers of oscillators that are firing. And then you get a straightforward way to write on the synchronization properties. For example, here you have whether the network of 4 oscillators is synchronized, or rather, what is the probability of finally synchronizing in this model. So there are some advantages, and one of them is that you may have different perturbation functions per oscillator. So each oscillator may have its own perturbation function, which is typically not considered, but still a possibility. You could also imagine that each oscillator may have a different probability to fail. So you can vary all these parameters within the network. Furthermore, you can actually model different topologies because you always encode the oscillators that may be perceived within each transition. That means you can, for example, encode star topologies, ring topologies, fully connected topologies, whatever you like. For the disadvantages, of course, what you have is that you run into the state space explosion quite fast. So in our experiments, it turns out that this is only feasible up to barely 4 oscillators. And this is, of course, because this is a very, very detailed model. So if we want to efficiently analyze models like these, we need to do something smarter, and something we came up with was, well, we took a closer look at the models actually and the applications. And it turns out that in most applications, the oscillators are not allowed to differ that much. Typically, they are all running the same device, running the same implementation of some kind of drivers software. That means they have the same cycle length. They have typically the same probability to fail. They have all of these similar aspects. And furthermore, it turns out that in applications, it's very often enough to actually consider fully connected topologies, because you're looking at things that are spread out over a very small piece of space. So they may actually be able to perceive all the other oscillators that fire. So what we use is something we called or framed population models. And in these models, we only keep track of the number of oscillators in each phase. So we're modeling the whole network directly. That means we ignore the distinction between the oscillators, and this is a very similar approach to counter abstraction techniques. So as an example, our states in this model are just tuples going from that contain integers from n1 to nt, where each of these n's is the number of oscillators that is in this specific phase, I. And intuitively, you can imagine that each of these states represents a cycle of length t, where each of the ni's is connected to the next one. And if we call such a state synchronized, if all oscillators are actually in one of these ni's. So it doesn't matter which one, could be n1, n2, n3, but all the other ones must be 0. That means that all oscillators share the same phase. Okay, so if we want to model that, of course, what you would do is you can create a DTMC where all the states are these tuples, where the sum over the numbers is actually the number of oscillators in your network. And you define a transition in two cases. First of all, if no oscillator is firing, that means nothing is in the highest phase, nt equals 0. Then all of the values are shifted from one step to the right. That happens with probability 1. Or if one of the oscillators is 0, then you actually need to see what kind of tuples are the successors of this state, and the probability of reaching one of these successors is determined by the broadcast failure probability and of the possible oscillators that may be perturbed but possibly can also fail. And you can compute both the probability and the number of cascading oscillators in a recursive fashion. So this is a bit more complex in its creation, and it also gets kind of lengthy because you need to explicitly encode all of these things in your DTMC, but it's actually feasible to do this with a Python script. And then you can actually use this Python script to automatically create loads of Prism models, start the analysis with different sets of parameters, and that's it. It is slightly less flexible than a concrete model, but you gain a lot in terms of efficiency, and you can even increase the efficiency by doing some other reduction steps that I haven't shown here, because the states where no oscillator fires, they are completely irrelevant for synchronization and so on. So you can basically skip them in the model. And it turns out that these two models are actually weakly bisimilar to another. So if you create a population model of the network, it is weakly bisimilar to the concrete model of the same network. Okay, so if we're going to more things than just purely synchronizing, it is really easy to define synchronization, but there are more interesting properties like how does the network behave during the process of synchronizing? So is there some kind of level of synchronization? And actually, for applications, it's very, very important how much energy it actually takes to reach a synchronized state. So for the first of these questions, we are introduced something that we call phase coherence, which is adopted from a model taken from traditional literature on phase-coupled pulse-coupled oscillators. And what it intuitively does is compares the distance of the different phases. If you again look at the cycle that we use in the population model, oscillators that are in opposing phases can be thought of as being further away from each other than if they are in two phases that are next to each other. One is the successor of the other. And you can actually do a computation like this of this phase coherence measure within the inline functions of Prism. And for the energy, what you can do is you can actually add reward structures to the population model where you associate different states with the idle power consumption and the transmission and reception power consumption from that you just take from a data sheet, for example, from the Mica Z mode. So when we've done both of these, and when you do this and actually put all of the results into something like R, you can actually get some nice pictures like these. I will not get into the details, but what you can see here is that whereas when the phase coherence increases, that means on the right-hand side, we have a fully synchronized system. On the left-hand side, it's barely synchronized. The power consumption, the expected power consumption increases differently depending on the refractory periods that you have. And in this, you see both the average and the maximal values. While on the lower picture, you see the time it takes for synchronizing the network. And you can see that while generally the average power consumption is proportionally to the time it takes to reach the same phase coherence, the maximal, the worst cases actually diverge a bit. So for example, a high refractory period of 4, it actually takes longer in the worst case to synchronize the system, but in the worst, still in the worst case, it will take less energy to synchronize to the same level of phase coherence. And that means this gives you now the possibility to actually judge trade-offs between what's important for your application, power consumption or the time to reach synchronization. What you can also do is you can analyze how the system behaves with different broadcast failure probabilities. And you can see that something that is a bit unintuitive, and that is if you don't have any failures in your system, or few failures, the synchronization worst case or the power consumption actually gets worse. Because then there are some problems that basically the oscillators chase each other around all the time. It's a very interesting thing. So actually, a less good model is better than a perfect model in this case, in this model, and this application. Okay, so what I've shown you is that we can all actually answer all of these research questions affirmatively. So we can model these discrete time pulse-coupled oscillator networks in the discrete time Markov chain. And with a population model, we can actually further analyze the whole system and actually avoid some part of the state space explosion. And we can furthermore use that to analyze properties that go beyond the yes/no question. Does the system synchronize, and what's the probability of that? Of course, there are still issues. We still run into the state space explosion, and you can actually, it turns out that the real killer here is not the model checking time, but the model construction time within the model checkers. So it might make sense to look at reusing models that have been used before. So using something like incremental approaches to model checking instead of recreating the models every time, or even going further to try to find some kind of inductive invariant that holds for any number of oscillators that we have in our system as long as we have X. And of course, it would be great if we find some way to actually go beyond fully connected networks for the population model. All right, thanks a lot for your attention.
So thank you very much, Sven. That's a very, very interesting different model of systems than what we often look at. So brilliant job of putting that across in this brief time. Let me first, I figured out how now, so let me first give you your certificates in the chat. And yes, that has been sent successfully. So there is an official for you and your co-authors available in the chat. I will send a copy by email as well. Thank you very much.
Thanks a lot.
There's time for a quick question for if someone wants to jump in. No, then we'll thank you again, Sven, and we'll move to the next speaker in